Okay, good morning. Good morning. Can you hear me? I'm changing this microphone from a wireless to this dot-ish, so I hope you can hear me, because wired microphones are always better than wireless, because wireless can run out of battery. All right, so welcome back to this class. So I hope the past week has been frightening enough that you see the skyrocketing speed of this course. This is done on purposely because that was the review. So what we're going to do today is to actually go into the material of this course. It's on probability. Okay, it's really on probability. So if you look at the book, you realize that we have a couple sections on probability until we talk about applications. Chapter 2 is really the foundation of everything that we need in 302. So what is chapter 2? I need to define what is probability. I need to define how a probability being calculated. Okay? Then I need to tell you some rules of probability. Those are called the axioms of probability. Then in chapter 3, we're going to learn a couple discrete time probabilities. So those will be the discrete random variables, counting, flipping a coin, throwing a die, those kind of probability events. Then in chapter 4, we're going to talk about continuous random variables that involves time, volume, those kind of applications, right? So in chapter 2, what we want to do today is to set up the ground. And there's a tool that we need. It's called a set theory. But before we go into this topic called the set theory, I want to do a mental exercise with you. Okay? What is probability? Okay, what is probability? Let's think about it in this way. What is probability? Of course, when you think about probability, it's going to be a number. Clearly, it's a number. It's a number between 0 and 1. Okay? 1 means that something is guaranteed to happen. For example, the sun is guaranteed to rise from the east. Okay, so this is a probability 1. Now, probability 0 means that it will never happen. Probability 0.9 means that something will happen very likely. So that's a number, which is good. But how do you get this number? How about let's throw a die? Very easy example, throw a die. What is the probability of getting a 1? 1/6. Okay? What is the probability of getting a number that is less than 5 and it is an odd number? Anyone? Less than 5 and it is an odd number. Anyone? Very easy. Yes? 2 over 6. How do you come up with this number 2 over 6? Okay, so there's 6 choices. Okay, so 6 choices. 1, 2, 3, 4, 5, 6. 6 numbers. I want less than 5. Well, less than 5 means that I do not include 5, right? Less than 5. So that would be 1, 2, 3, and 4. And then I want odd numbers, right? Odd numbers. So I want odd numbers. And then what do you do? Well, you look at this list of numbers and you say, okay, that's 1 and that's 1. Out of the 6 possibilities, this is 2 over 6. Okay, so this is the very simple calculation. All right, but there's actually a lot of things involved in this. A lot of things involved. The first thing is, why 6? Why 6? Well, you say, look, you have a die, you 6 faces. That's why you get 6. But there is actually a concept here. It's called the sample space. The sample space is the set that contains all the possible outcomes. Okay? All the possible outcomes that you can ever think about in this experiment. Okay? If I'm not doing throwing a dice experiment, I'm flipping a coin. What is the sample space? Okay? 2. Very simple. You see that there is a sample space involved. There is a collection of all the possible cases. Then what do? Then you look at the description I gave to you, less than 5, and odd number, right? I'm telling you two statements. I'm telling you two statements. The first statement is that less than 5, which is a subset inside the set. Okay? Now, if you're new to this notation called set is nothing, but it's just a bucket. A bucket that contains a lot of things. That contains elements. And then I'm saying that, okay, let's look at this bucket. Inside this bucket, there's a smaller bucket. There's a sub-bucket, a subset, that contains elements that are less than 5, which would be 1, 2, 3, and 4. It's one set. Okay, so that's one set. That's called A. This is 1, 2, 3, and 4. One subset, okay, inside this big set. And the set, let's call it S. Okay? And then I say the second statement, which is odd number, right? Odd number. So the odd number would be 1, 3, and 5. I'm telling you another subset inside this set. Then I say and, okay? I want less than 5 and odd number. So there is an and operation, which is given by this notation, A and B, right? A and B. And so this A and B is going to look for all the elements that are in the overlapped subset. Are you following me? I'm looking at the and. So 1, 2, 3, 4, and 1, 3, 5, it will be 1 and 3. That is common among the two. And so I can come up with this 1 and 3. Okay? So that is giving me an event. An event is one. An event is a subset in the sample space. An event. Okay? Now, the event can be single element. The event can be a combination of elements. The event can be constructed from two other events, event A and event B. I can construct an AND operation. I give you another event called A and B. Right? And I can talk about what is the probability of getting that A and B. I was inside the set of S. Right? So now there's already two notions, right? The sample space, the event. There's a third thing, is the assigning the number. Assigning a number from an event, okay, to a number between 0 and 1. And that assignment is called the probability law, okay, or the axioms. So the probability law is going to be that I'm going to look at this event, which is a set contains 1 and 3. I measure the size of this event relative to the size of the sample space. Okay? And so what is probability? Probability is a measure of the size of a subset inside the sample space. If you forget about everything of this course, remember the statement. What is probability? Probability is a measure of the size of a subset inside the big sample space. Okay, you need two measures. One is to measure the size of this sample space. The other one is to measure the size of your event. Right? And that's the ratio that defines the probability. So you say, why do you want to abstract things in this complicated way? Throwing a die is just that simple. Why do you need to abstract things in that way? Well, today we're talking about throwing a die, flipping a coin. Tomorrow I can give you a bucket of water. I say, what is the probability of getting a water between 1 mil and 3 mil? Okay. Well, then you say, okay, well, how do you do that? You have a big bucket, you have a small cup, you take one cup out. I can say the probability, okay, is the relative size of your event and also the sample space. I can talk about functions. Inside this big bucket, the bucket can contain a lot of different functions. A cosine function of different frequencies. That's random process, right? So I go into this bucket, I pull out a function. I pull out a set of functions. What is the probability of pulling out of these functions? They're all sinusoid functions, cosine functions of wavelength of certain number. Right? I ask, what is the probability of pulling this set of functions? Right? That can be measured by probability. And so when you think about probability, what is that probability? Probability is always started with measuring the size of set. And that's why, as we talk about probability, we need to talk about set theory. Now, I know some of you in this classroom have already learned the set theory, Some of you haven't learned the set theory, and so we need to go into the details and learn about what is the operation that we can apply to different sets. Here is a very simple case of AND. We can do OR, we can do NOR, we can do different kinds of set operations. We can form an infinite combination of sets. You can take an infinite AND or infinite OR. How to define those? Okay. Now, if I give you 2n, I put a complement outside, how do you do the set operation? Right? So all these different kinds of combinations, we need to know the theory behind them. So that's the purpose of the set theory 2.1. Okay, so now if you look at this outline, you can see that we have 1, 2, 3, all the way to 8 subtopics. Okay, so each one will be fairly short, but they contain a definition and some theorem and also some examples. As you're studying across these 8 subtopics, my advice is to make sure that you understand the definition. Make sure that you understand the definition. Make sure that you can draw a picture. Whether you can sit down and write the proof, that's more advanced. Okay? It's more about whether you can draw the picture, whether you can associate the argument with the picture. So let's get started. What is a set? There's a formal definition. A set is just a collection of objects. We're going to use this notation called A. It's a capital letter that contains a finite set of elements. Now, of course, a set can contain an infinite number of elements. But here, I'm just saying that a finite set will contain all these numbers, psi 1 through psi n. Okay? It's just a bracket that contains n elements. I call this a set. Psi I is the ith element of the set. Now, I have different notations in case you haven't learned them before. The psi in A means that an element psi is in the set A. I put this not in A, that means this element is not in the set A. Okay, so that's a notation I'm going to use. A set can be finite, can be countable, can be uncountable. Countable means that finite means that you only have a finite number of elements, 0 or 1, 0, 1, and 2, 1 to 6, 1 to 10, 1 to 100. So that will be called finite. It's countable when you can go to infinity, but you can still count them. For example, the set of all the even numbers, the set of odd numbers, those are countable events. They can be uncountable. For example, you're talking about time between 0 and 1. So that's called an uncountable set. Now, I also have this notation. There's an open and closed interval. This is more useful for continuous random variables. I'm going to define this open bracket as x between a and b, not including a and b. If I put a square bracket, it means that x is between a and b, including a and b. And of course, we can extrapolate this notation to say a, b, a open, b closed. So that is going to be x between a and b, including b. Right? So I can do this semi-open, semi-closed interval. All right, so this is the definition of a set, and you have different examples. And here are 2 examples that are less obvious. Okay? Of course, we can think about flipping a coin, throwing a die, those kind of experiments. But a set can contain functions. This is what I've been saying. This is a set of all the possible straight lines that you can draw in a 2D plane. Now, how do you do that? Anyone has a thought? How can I write down the set of all the possible straight lines in a 2D plane? How do you do that? Yes? ax plus b, excellent. Okay, so define this function y equals to, let's call it fx equals to ax plus b. This is a set that contains all the possible functions that's defined by this ax plus b. I only need 2 parameters to specify all the straight lines. Okay, a will be the slope, will be the y, will be the y-intercept. Okay, so that's b. As long as I can tell you a and b, you can define the straight line. And I can say, well, you have more probability. The probability of getting an a will be more concentrated as slope of 1. Okay, and then there is some kind of probability that you can go to 0.5 and plus 0.5 or minus 0.5, but you will never go into minus 1. Right? So you can define the range of A. Similarly, you can define the range of B. That will constrain the set of straight lines that you can use. For example, you say, I only want positive slopes. Okay? And the positive slopes has to be around 1. Then you can define the range of A and B accordingly. You can even say the probability of getting an A will follow certain kind of distribution. It could be a normal distribution centered at 1. You can define it that way. Right? So that will give you a set of lines. Maybe it's all about that. Okay? It's all about, with a slightly slope of 1 and minus plus 1. You know, they're fluctuating, but they're mostly there. Right? You can define it that way. This is a set. This is a set that is parameterized by 2 parameters. Although when you try to write it out, you have infinitely many choices. However, when you try to describe them in math, you only need 2 parameters. Very simple description. This is another example. This is a set of all the cosine functions with unit amplitude. I'm just changing its phase offset. I'm not changing its wavelength. I'm changing its phase. Now, what is phase? Phase means that I have this cosine function. I move it to the right, to the left. This is called a phase. All right? So I'm changing the phase. And then the phase is, of course, between 0 and 2 pi. So can anyone give me a suggestion of how do I describe the set of this set of functions? It's a set. Right? It's got to be a set. It's got to be a, yes. Okay, how about cosine 2 pi x plus theta? Okay, cosine 2 pi x plus theta. This theta, of course, it has to be between 0 and 2 pi. Right, so I can define the sets accordingly. Now, this x, of course, it will just be this x-axis. It's just a dummy variable. The randomness is defined by this theta. Okay, now this is another thing that you need to be very careful. Whenever we talk about probability, random variable, random functions, stochastic processes, there is always the source of randomness. Okay, there's always a source of randomness. The source of randomness in this cosine function is the theta. The 2 pi x is not random. Okay, x is, of course, from minus infinity to infinity. It's just a straight line in the time axis. Theta is the random variable. Theta is the randomness. Theta is the source of randomness. Here in this set of functions, a and b, this a duplet. Okay, this pair of numbers, they are the source of randomness. Okay, I flip a coin, throw a die. I can tell you the random realization of a and b. They will give you a different line. Okay, I give you a different theta, you get a different cosine function. So this is the definition of a set. The set can be very, very general. I see the question. Do we need to have a description of how the parameters are bounded? Yes, of course, of course. So to be more precise, when I define this A, that is the set that contains all the fx, which is ax plus b, I also need to tell you what would be the range of A and B. For example, I can say A is between minus 1 and 1, and then B is bigger than 0. Right? I need to tell you those parameters. If you do not tell me these parameters, I will just assume that they live in the real line from minus infinity to infinity, if you don't tell me, right? But if you tell me, then I need to follow this definition. Correct, correct. Will the bounds of A and B be considered as part of the A set? Correct, they are part of the A set. However, the set A, is not a set of A and B. This set is a set of all the straight lines. Okay, this set is the set of all the straight lines. This set B is a set of cosine functions. I want to make it clear. It's not a set of theta. It's a set of cosine functions. Think about you put a bucket here. You put your hand into the bucket. As you draw things out, you're not drawing a theta. As you draw things out, you're drawing the cosine function. There can be multiple random realizations that can give you the same function. That's possible, right? For example, I have an absolute value of ax. Absolute value of ax, right? I can give you a equals to 1, a equals to minus 1. I can give you the exact same function because you put an absolute value, right? So therefore, the set A is not the set of parameters. The set is the set of all these functions. As you were learning the set theory, I guess the usual way of thinking is apple and oranges, 1 to 6, a die or a coin. But I want to make sure you, starting from today, think about the set can be extremely, extremely general. Think about the functions. There's a bucket, put a hand in, you put a function out. You put a function out. You're not putting a number 1. You're not putting a number 2. You're putting an entire function. As you put out, it's the entire cosine function that's oscillating. Think in that way. Okay? That's going to change the way you think about the probability. Okay? All right, so that's the set of functions. Subset, of course, is a smaller collection of elements inside the set A. And we can write B with this notation in A if for any element assigned in B is also in A. Now, that's very easy to understand. Let's say this is your A, and then here is your B. We say that B is in A. Okay, B is in A. If you pick any element B, it is also in A. Then we say B is in A. Okay. Now, let's say this is B, this is A. Then B is not a subset of A because I can pick an element that is not necessarily inside A. So B is not a subset of A. This notation, the way to think about it is that it is less than or equals to. Just put this analogy. Okay, so this is a set less than or equals to sign. When will you get this equal to? Just think about the open set and closed set. Right? So think about open set and closed set. You can say, okay, I define the S equals to 0 and 1, and then I define an A event of 0 and 1. Then you can say, okay, A is a proper subset of S. Now, of course, it's the same, but you can define it that way. So there's a theorem here. If A is less than or equals to B, A and B is less than or equals to A, then of course A equals to B. So that's very easy to prove. There's a notion of proper subsets and an improper subset. A proper subset means that all the elements in B is contained in B. Okay, they're less than B. An improper subset means that B can be equal to A. B can be equal to A. All right, so the proof, I can skip that, but I think as long as you can draw this figure, I think we are good. There is a notion of empty sets, and there's also a notion of a universal set. An empty set, of course, as it is called, it just doesn't have anything. But pay attention to this empty set. It is a set. Okay, I call A equals to this. This is a set. Okay, empty set is a set. Empty set is not 0. The size of empty set is 0, but the empty set is not 0. Is it clear? All right. Now, you can also form a set of sets. Now, what do I mean? So you can have A1, A2, all the way through AN. These are all sets. Okay? I can form a set of sets. That's complicated. Okay, so each one is a set, but then you can call that because what is a set? A set is a collection of elements. There's just a collection of a lot of things, and of course, inside this set, this bucket, you can have many small buckets. That is well defined. Okay. All right, so let's go back to here. You can have an empty set. You can have a universal set. That universal set is just our sample space that contains everything. That contains everything you can think about. You need to define the universal set, but sometimes it's assumed to be the entire real line, or sometimes it's assumed to be 1 through 6. It's really defined by the problem. Okay? Once you have the problem in hand, you know what you're talking about. You're looking at time, it will be from 0 to infinity. You're looking at an area, it's from 0 to infinity. You're looking at score, okay? Final exam score with 0 to 100. So this universal set is already well defined by the problem. Okay, so now let's talk about operations, okay? 4 and 5, 2.1.4 and 2.1.5, union and intersection. To just help you remember what is union, union is or. Intersection is and. Okay? All the set operations is defined by three things: or, and not. Okay, we're going to talk about those. Okay, so let's talk about or and. As long as you have or, and not, you can define everything. It's just a combination of these three operations. Okay, so let's talk about or. What is or? Ignore the definition for a while. Okay, let's just do a very simple exercise. You have set A, which is 1, 2, 3, and 4. Set B, 1, 5, and 6. What is the or? Okay, what is the union of these two sets? Well, it got to be the set that contains both A and B. Right? So it got to be 1, 2, 3, 4. That's coming from A and B. So 1, 2, 3, 4, 5, 6. Okay, so that would be the or. So what is the definition? Let's go back to here. This union of A and B would be the set that contains all the psi, where the psi is in A or the psi is in B. Now let's go to this example again and see if it makes sense. I have an element. Let's say I have this element 1. Does it belong to A or B? Of course, it belongs to A. Does this element 6 belong to A or B? It doesn't belong to A, but it belongs to B. Right? Or, right? Either one will be fine. How about this element of 0? Does this 0 belongs to A union B? No, because 0 is not in A, it's also not in B. So 0 is not an element in this A union B. Very simple. Okay. How about this event? A is bigger than 3, but less than or equals to 4. B is greater than or equals to 3.5. Anyone want to make a guess? Yes. T has to be T has to be bigger than 3, right? And then it should be less than or equals to 4. Oh no, sorry. Yeah. Okay. So this is A union B equals to this set. T greater than 3. Now why? Okay. So let's draw it. So the set A will be between 3 and 4, right? And then B will be the set that is bigger than 3.5. I need to take an or, right? So here I'm taking this shaded area, and then here I'm taking this shaded area going to plus infinity. I'm taking the or, and so it will just be anything bigger than 3, it will be the or of these two events. Is that clear? Okay? Good. Now, there's something more trickier. It's called infinite union. Now, that's something that you haven't seen before. Okay, infinite union. And infinite union has this ugly notation where n goes from 1 to plus infinity. Now, how do we define this operation? Well, you say that this element x is in A if x is in at least one of those n sets. That's the definition. Okay, so you go to this infinite union. How many sets are there? There are infinite sets in this infinite union. Okay, so there are infinitely many sets. You go to each individual one, one at a time. You ask whether this element is inside at least one of those. If yes, you say this X belongs to the infinite union. Okay, so let's work on the example to make it clear. Now, this example will take some brain power to digest. Okay, so follow me. There is a sequence of sets, AN, which is defined by this closed interval. The left-hand side is 0, including 0. The right-hand side is 1 minus 1 over n, including 1 minus 1 over n. And then AN is defined by this interval. And so now what is A1? A1, can anyone tell me, what is A1? A1 is 0. How about A2? 0 and half. A3 is 0 and 2/3. Okay, so you can start growing the set. Where will this number go to? 1? Okay, 1. Okay, so 1 is a magical number. 1 is a magical number. I guess we don't have to debate anything less than 1. Okay, anything less than 1, I don't think we need to debate because 0 is always inside, right? As we are constructing this infinite union, 0 is always there, right? So the 0 got to be in the set A. 0.01 got to be inside because it's there everywhere. Okay, it's there at least in some of the sets. Okay, how about 1/2? 1/2 is there because 1/2 is already here. 1/2 is actually over here as well. Okay, so I think among the numbers from 0 to 1, anything less than 1, we're pretty safe. We say that there's 0 and 1, they're all fine. They're all fine. We just need to worry about this magical number called 1 to determine whether it is 0 or 1 closed bracket or 0 and 1 open bracket. Are you guys following my logic here? Okay, between 0 and 1, not including 1, everyone should be included. The only thing that we need to worry will be whether 1, that number 1, should be included or not. Is it okay? Okay, let me see. You are okay? All right. Next question? Okay. All right. So now, whether 1 should be included or not. Whether 1 should be included or not. 1 is not included. 1 is not included. Want to make a guess? Why 1 is not included? Exactly. Okay, do you guys hear? So let's look at this number 1. This is number 1. This 1, it doesn't belong to any of those, no matter how big your n is. You make the n equals to 10 million, you are still not include that number 1. You're still 1 minus 1 over 1 million, or 10 million. You're still not including that number 1. So no matter how big your n is, your 1 is never included. It's never appear in at least one of these A1 through AN. Therefore, 1 is not part of this infinite union. And so the answer is this. Okay, so this is the infinite union. The infinite union, even though you start with all the closed sets, as you put together, you look at the final end point, this is the 1, is not included because this number 1 is not included in any of those intervals that you're considering. That's called the infinite interval. Okay, and so the answer is B. Similarly, we can define the notion of finite intersection, which is the case of AND. Right now, for AND, it's also pretty obvious. You want to make sure that you are looking at the overlapped elements inside the set A and B. So in this example, 1, 2, 3, 4, and 1, 5, 6, the A and B will be 1. Excellent. Thank you. Okay, so this is 1. For this event, t between 3 and 4, including 4, and 3 bigger than equals to 3.5, it will be anything, and let's just draw it, okay? So this is 3.5, 3 and 4, and here it will be 3.5. So the end will be anything you start with 3.5, you end with 4. Okay, so that is your A and B. Okay, now if you want me to write it out, it will be t less than 4 bigger than 3.5, including 3.5 and 4. So that would be the set. That's the N. So this is pretty easy. Now, how about the infinite intersection? Infinite intersection. Now, recall the definition of infinite union. You got to make sure that an element is in the set, in at least one of the sets. Right? In at least one of the sets. That is OR, right? So think about OR. What is OR? You have A and B, you got to be at least in one of those, right? Therefore, if you have infinite of those, you just try to make sure that X is in at least one of those. How about AND? Well, if you think about two sets, A and B, you want to make sure that an element is in both A and B, so they need to appear in every one, okay, that you're considering. And therefore, for this infinite intersection, you want to make sure that X is in all of these A1 through AN. It's in all of A1 through AN. So let's consider this example here. You have the sequence of sets, which is closed on the left-hand side, 0, open on the right-hand side, 1 plus 1 over n. Okay? So again, let's try to write down a few cases. So A1 is 0 and anyone? A1, I just put n equals to 1. This is 2. Okay, great. How about A2? 0 and 1/2. Okay, 1. Okay, and then A3, it will be 0 and 1 and 1/3. Okay, so as n becomes bigger and bigger, where will the right-hand side go? Start with 2, 1/2, 1 and 1/3. Where will it go? Yes? It will approach 1. Okay? So again, I guess we're pretty okay with the number between 0 and 1, excluding 1, right? 0 and 1, everyone should be okay. The magical number is 1. Should this 1, okay, should this 1 be inside this infinite intersection? Yes or no? Let's raise our hand. How many will say yes? Okay, how many of you will say no? How many of you will say, I don't know? Okay, good. Thank you for the honesty. I like that. Okay, so let's do some mental calculation here. Well, I'm looking at all these n sets, right? I'm looking at this magical number 1, right? Everything else, I think we're all okay, except for the number 1. The number 1, is it in A1? Yes. Is it in A2? Yes. A3? Yes. No matter how big the n is, your 1 is always inside. Therefore, this 1 is included. Okay? And so the answer is this one. Question? Is X 1? X is not 1. X is not 1. This X can be 0. This X can be 0.12. This X can be 0.37. Right? So for every number, basically I'm doing a check. For 0.12, I check, well, is 0.12 is inside all these? Yes, and therefore 0.12 belongs to this infinite intersection. Is 0.97 belong to this infinite intersection? I check 0.97. Yes, 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 yes. Everyone is yes. So I say 0.97 is inside the infinite intersection. So basically, you just need to check through everyone. But basically, for number between 0 and 1, excluding 1, we're all good. We're sure that they're inside. It's just that the number 1, we're not sure. Question?
So if A in this example was inclusive on the right side, would our answer have to be exclusive on the right side?
You got to check this based on this definition. Okay? It's not guaranteed. Okay? Now, what you're asking is, what happens if this is a closed bracket? Okay? What happens if this is a closed bracket? If this is a closed bracket, we can do this, right? You can keep doing. So A4, right? So you just keep doing. Is this a 1 included? As you go down the list, 1 is included, and therefore your infinite intersection will still be the same. Right? You just need to check whether it is inside every possible set that you're constructing in the sequence. Make sure that they're in, then yes, the limit is also in. Okay. Now, if I change this to minus, it's a different story. Right? So you just think about if I give you a plus, now you change to minus, is it still inside? Well, it actually turns out that it is no longer inside, then it becomes an open bracket. Right? So think about different ways of understanding the problem. The infinite intersection goes from checking all, and then for the infinite union, you check for at least 1. Okay, so that is the way to check all these sets. Now you may wonder, why do we need to talk about these? It's just because a lot of random events, you cannot count them. You just cannot count them, right? Flipping a coin, throwing a die, yes, you can count. But as soon as I talk about time, as soon as I talk about water, as soon as I talk about volume, area, you cannot count, then you need to have, mathematically, you need to have this kind of notion of countable events to take care of these infinite sequence. Is it all right? Question?
I have a question. So if the 0 in our set, as of right now, becomes a 1, will we end up with an empty set?
Okay, good question. So let's do it. Okay. So if this AN is 1, do you want open interval or do you want closed interval? Oh, okay. So let's do the closed interval first. Okay. So let's do that. So 1 plus 1 over n. How about open? Okay, let's just try it. Okay, open. So we ask, is the infinite intersection, does it include this magical number 1? Does it include magical number 1? Right? So I use A1. A1 is 1 and 2. A2 is 1 and 1 1/2. Right? As I'm illuminating all the possible cases, is this magical number 1 belong to every single AN? The answer is yes. The answer is yes, because I look through everyone, this 1 is there. Yeah, the 1 is there. Now, if I change this AN to open, then it's a different thing. Is this 1 included? Let's think about that, right? Let's think about that. Is this 1 included? So now you're not including the 1 on the left-hand side. So here you have A1 equals to 1 and 2, and then A2 equals to 1 and 1/2. You keep doing, and then AN, it will be maybe 100, it will be 1 and this. Okay? Is this 1 included? Is this 1 included? No. Because where's 1? 1 is actually outside the set. 1 is outside the set. So as you squeeze it, what do you get in the limit? You get empty set. That's what you're describing. Okay? You get empty set. So it all depends on how you construct these sequences. And it could be that at the limit you get an empty set. Because in this case, your 1 is outside. Does it answer your question? Yeah. Okay. More questions? Okay. Good. All right. So now let's also talk about complement and difference. So as I said, there are literally 3 operations: and, or, and not. Okay, not. Now let's talk about the not. So what is not? Well, that's easy. If A is a set of integers even integers, the sample space is the set of integers, then the complement, which is the not, it will be odd integers. Trivial, okay? Now, one thing I need to specify is that you need to tell me what is the sample space. You need to tell me the universal set. Otherwise, I cannot define the complement. Let me give you an example. Here, if I do not tell you the omega, what is the complement of even integers? It's actually you don't know. If it could be the real line. Now, if it is a real line, it could be all the numbers on the real line without the even integers. That's a pretty big set. Okay? All right? It's not just the set of odd integers. It could be all the real numbers, including rational, non-rational numbers, as long as they're not integers, they're not even, they are in the complement. All right? Now, if you make it into complex line, that's even more complex, right? And that's why I don't like complex numbers, because it's just too complex. All right? So you see that you got to tell me what is the universal set or sample space. Otherwise, I cannot define what is the complement. Now, if you know the sample space, then the complement would just be whatever that's not inside, but is in your universal set. So that's defined this way. There's a notion called a difference. Difference, depending on which textbook you read, sometimes people write this A/B. Sometimes people write A minus B. It's the same issue. So you have, let's say this is your A, this is your B. A/B means you want A, but you don't want B. Okay? You want A, but you don't want B. All right, so the stuff inside is called an A intercept B, right? This half moon on this side is called, you want A, but you don't want B. Okay, you want everything that's in A, excluding the parts in B. You don't want it. Okay, so that is A without B. Here, if this is A and B, this part is B without A. Okay, so that's called the difference. Now, that's an interesting thing. If you look at A no B and B no A, these two sets, they actually do not overlap. Okay, these two sets, they actually do not overlap. And so there's a name for those. They call disjoint. So let's say I have this set, and then I have this set. I call this set A, I call this set B. They are not overlapping, and therefore I say that they are disjoint. For example, here, this is A, this is B. They are disjoint because there isn't any overlap between the two sets. And so we can have A less B and B less A are disjoint. Okay, so now if you have a set of, if a sequence of sets, you can say that they are disjoint if any pair is disjoint. Okay, so I guess we will stop at this point. And as we come back on Wednesday, we can review this notion of disjoint, and then we can talk about partition. Then we can move on and talk about different set of operations. Okay, so I'll see you on Wednesday.